Next on our list are retroreflective sensors. Unlike through-beam sensors, which have the emitter and receiver housed in different units, retroreflective sensors have the emitter and receiver co-located. Once the light is emitted, it will travel across the detection zone and bounce off a prismatic retroreflector. The receiver will then detect that the light has returned. Once the light beam is broken, the sensor will indicate that an object is present. What makes retroreflectors unique is that they will always reflect waves directly back towards the source. This makes alignment easier, as the sensor doesn't need to be perfectly perpendicular to the reflector. What if something shiny passed by and reflected the beam back to the sensor? A standard retroreflective sensor wouldn't be able to see or detect the object, but a polarized retroreflective sensor could tell the difference. Normal, unpolarized light oscillates or vibrates on multiple planes. It's unpredictable and non-uniform. To create linearly polarized light, the vibration of the electric field and magnetic field must be perpendicular to each other. When we take the average of these two fields, we could draw a new vector which represents our light wave. As you can see, our light wave is now oscillating on a flat plane, so it is linearly polarized. If our sensor emits linearly polarized light, which is oscillating on a vertical plane, that light will travel across the detection zone and bounce off of our retroreflector. When this happens, the polarization of the light will rotate 90 degrees. Our light wave, which was vertical, has flipped horizontal and makes its way back to the receiver. The receiver is trained to look for polarized light, which is 90 degrees rotated from when it was emitted. When this happens, the sensor knows that no objects are present within its sensing area. So how do you tell when a shiny object enters the sensing area? When polarized light bounces off of a reflective surface that isn't a retroreflector, the orientation of the polarization doesn't change. A vertically polarized light would remain in that orientation as it made its way back to the receiver, and would be invisible to the receiver since it was only looking for horizontally polarized light. The only reflective object that could fool the sensor would be another retroreflector. The standard S100 retroreflective sensor has a sensing range up to 7 meters, with the polarized short and long range models offering a reduced maximum range of 3 to 5.5 meters due to the light loss of the polarized filters.